right? Those distinct lines were the evidence that Bohr went through and said, that means our electrons have to exist at distinct steps, or orbitals. Right? And so when he went through and did it, we could go through and say, well, how did he know that there were 7 orbitals associated with it? Right? And we might say, well, because of all the little jumps, he could figure out the energies. Remember, we can't see these things. Right? So how did he decide that there were 7? Okay. Talked about nuclear physicists and the study of atoms, like getting down real nitty-gritty detail. Okay. You're looking at quantum physics. You're looking at how we solve the equation to describe how an electron moves. Okay. And really how an electron exists. So you're looking at mind-bogglingly difficult calculations. For those of you that think you've had hard math, you probably aren't even scratching the surface. Okay? They invent new notations to explain the mathematics, to explain what's happening within this. And when they go through and solve those equations, they've noticed that certain patterns come out. And we get possible energy levels between 1 and 7. We could theoretically go higher than that, but then we run into a limit. What is that limit going to be? Okay. If I hold my pen really close, that's reasonable. If we slowly start to move that pen further and further away from me, what happens eventually?
Drop it.
It goes out of my reach. I can't hold on to it anymore, right? Same thing's happening with electrons. Our protons are that nucleus, is that hand holding the electrons in. Eventually we go out to a high enough energy level that it is so far out there that the nucleus can't hold it anymore. And those electrons have now disappeared into what is known as the vacuum, because there's now nothing out there. So our upper bound on this is the vacuum. CCU. There you go. Okay. So we've got these energy levels. We then start to interpret those energy levels and look at the physics and look at the quantum mechanics to establish the different kind of numerical values that can possibly come out of it. Okay. The first set is just these energy levels. Okay. Where are the energy levels reflected in our periodic table? Well, I got 1, 2, 3, 4, 5, 6, 7. That corresponds to the rows on the periodic table. The first row that has hydrogen and helium is the first energy level. The second row, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, helium, is our second energy level. Okay? So on and so forth all the way down. And you might say, but aren't there 9 energy levels? Okay? Because there's 9 rows, right? The lanthanides and the actinides, starting at the very bottom, La and Ac, there's stars next to those. Those are technically inserted into the table above, which means we don't have an 8th and 9th row. They're actually part of the 6th and the 7th row.
They just extend further out.
If we had inserted them into the periodic table there, what would then happen?
It would make more groups.
The periodic table would then have to stretch and get really, really, really long. Okay? Why did we not do that?
It's ordering.
It's not aesthetically pleasing.
It is not aesthetically pleasing.
Yeah.
Okay? By setting it up in the fashion that we currently have, it looks a little bit more kind of square-ish, a little bit more compact. It's not as difficult to deal with. Taking a step further, the lanthanides and actinides. Our actinides, that AC row, I can't do math that fast, but 80%, 80 to 90% of them are all man-made. Okay? How often are we going to deal with those? Not often at all. We even move up one row above that, our lanthanides. Most of those are at least in existence. We didn't have to man-make those. Okay? But they are super, super active as elements on their own and in very small concentrations, which makes them super rare, super expensive, not likely to work with. Well, if they aren't likely to work with, do I really need to emphasize their location in the periodic table? No. And that's why they get pulled out, because by inserting them, it makes what it can potentially already be a confusing periodic system much more confusing. So we just pull them out kind of separated away from it, but realize they're inserted in. So that's our 7 energy levels. Okay? So we do have that evidence to support that in our periodic table. So our periodic table is already organizing electron orbitals. Okay? What happens if we took other elements? Well, if we take in, say, helium next. Well, what happens with helium? When I move from hydrogen to helium, what's occurred?
I've added neutrons.
I've added neutrons. What else did I do? I added protons. Are the protons going to change, or having more protons going to change how that first electron sees the nucleus? Yeah, it's now a stronger positive charge. That first electron, when I first put it in, is going to have a different energy level than, say, the hydrogen, which then means all of the subsequent 7 other energy levels are now also different. Okay? Which means when we go through to look at our atomic line spectra and we look at how the electrons can move through the structure, we will start to notice that they do not overlap. We have effectively fingerprints for each of these. Every element has a distinctly different number of protons than every other element, which is going to change how they see their electrons, which then means the electron energy levels are going to change, which then means the jumps between those energy levels will also change. Hence, we see different line spectra. Kind of, sort of? Kind. So they've got some examples shown there. That's kind of it. They're often referred to as the atomic fingerprint because each element has its own characteristic line spectra. Okay. What could we do with line spectra? Okay. Well, we could aim a telescope out at the furthest reaches of the universe, and we could look for line spectra. Well, why is that important? Well, what did you just find out there? We could identify new planets. We now know something about their elemental composition because of those line spectra on the light that's making it back to us. Okay? So we can use atomic line spectra outside of chemistry. We could also use it to, I don't know, make our bars look really colorful by putting in neon lamps. Okay? Those neon lamps getting those different colors are because different elements have been put in and been cattle prodded, which is getting different colors. Okay? So, our electron home. So let's go through and look at what Bohr went through and did. Okay, so we've got, I'm not sure I counted this right, but we'll see what happens. We've got our nucleus all the way down at the very bottom. Okay, down here. There's our nucleus with all of its protons.
So when you see like lightning strike, is that just like that energy just like riding up
Okay.
all the
Dominic,
atoms it
I
goes
believe Dominic had a question about this before. We see a lightning strike, right? What's happening with that lightning strike?
Aren't there 2 different types where one leaves the planet and goes up, or
So there's
comes down from
varying forms of where the lightning starts and originates from, but ultimately it's all going to the same thing. We've built up an imbalance of charge. We have a density or an area of very high electron density and an area very low. Well, high electrons don't want to just chill there. That's why when we stick our finger in the electrical outlet, what do the electrons do?
They go in the
They flow through us and into the ground to neutralize. Okay, so if it builds up in the atmosphere that we have this high electron density, what happens? They
comes down.
start to find a place where there's a low density of electrons. And they'll go, oh, it's time to move. And so they will move to the other spot. And in the process, what do they impact? All the other air particles. So any air particle that's in the way, guess what? Just got 22,000 volts put through it. What does it now decide to do? Release that energy as light. Okay? Why do our lightning strikes look blue or whitish?
Because it varies on like what's in the air.
Look at the elemental composition of our air, nitrogen and oxygen, and cattle prod pure nitrogen and oxygen. Guess what color you're getting? Blue and white. Okay. If we lived in an environment where it was all neon, guess what? The color of our lightning strikes won't be white or blue because we're now getting the color characteristic of our neon, which is, I think, a yellow-orange, but I don't remember exactly. Okay. So back to our electron home. We got our nucleus chilling at the bottom. We have our first energy level, and then we have our vacuum all the way up at the top. Okay? The vacuum Okay. VAC. I didn't get it. You told me.
You just gotta have confidence behind it.
I put 2 C's in it, so I don't think it counts to reference my
I always do that
confidence.
the first time anyways.
So we've got our vacuum, and then we have our energy levels get added into this. Right? What do we want to call our first energy level? Why not 1? Ta-da! There it is. Our first energy is called energy level 1. What's our second energy level going to be called? 2, and 3, and 4, and 5, and so on. So what we end up with is our stack of our energy levels. And we could go through and now label these. Okay, 1, 2, I'm not going to label them all, but I'll go up to green. 3, 4, 5, 6, 7, right? Till eventually we reach the vacuum. Notice that how are these stacking?
The gap is
Tighter and tighter.
yeah, tighter.
The gap is different. Why would the gap be different? Well, what are we putting into these? What goes into the orbital? Electrons. Okay. As a lower energy orbital, where is that electron going to be? Closer or further from the nucleus? It should be closer so that it can neutralize that be neutralized by that positive charge, right? If I look at a sphere and say, okay, I put an electron here. The next electron, where should it go? Should it go in at the same spot?
No.
Why not?
Can't exist at the same spot.
Can't exist at the same spot. What are you suggesting over here? No, I don't quite accept that either. 2 electrons. Their charges are the same. It's going to repel. So what's going to happen? That next electron has to go further out. Right? By going further out, also our radius is now increasing. Okay? So we start to see kind of that shift further and further out. The closer it is, the more that electron kind of shields it. The next energy level has to be further out. Okay? So we see that jump. Why does it continue to get smaller up at the top?
It's almost like volume, like because the ring is getting so much bigger.
Can I continue to move the pen further and further from my body through to infinity? No. What's the limit? Vacuum. I'm no longer holding onto the pen. Same thing happens with our electrons. As we move those further out, we eventually reach a limit. We have to keep kind of getting closer and closer and closer to each other for that energy level. Kind of make sense? Okay. So let's go through and start to fill our orbitals as we've just discussed. Okay. I'm going to arbitrarily decide to draw my electron as an arrow.
So does it take less energy or more energy to go from the 6th to the 7th than it would from the 1st to the 2nd?
Okay, so let's, because 6th and 7th aren't labeled here, let's change that. Does it take more energy to go from the 1st to the 2nd or from the 2nd to the 3rd? The 1st to the 2nd is a larger jump than the 2nd to the 3rd.
Yeah.
Same thing's going to happen all the way up. As you continue to go, that gap becomes narrower and narrower and narrower.
Or it just takes less energy.
It becomes less and less energetic to make that jump. Yes.
And there is only 7 energy levels.
There are only 7 energy levels that, admittedly, we have discovered. We add one more, what's the word? Electron and proton to make the next element, element 119. We're now moving to, technically it's not even actually the next energy level. We'd be moving to our next tier up, which could theoretically be the next energy level. Okay? But we'd have to keep adding more stuff to it. We've kind of reached that vacuum level where we can't get any further because we add any more stuff to it, what happens? It's now so far away it's not holding on to it anymore. If it's not holding on to it anymore, we no longer have an atom. Does that make sense? So theoretically it could go on to infinity.
So then if you like put that electron to it, it doesn't like react to it because it can't, so it just goes around looking for something else to react to?
Yep, exactly right. Okay, so back to our electron. Everybody okay with my little arrow?
Yeah.
That is our first electron, right? Okay. So where's the second electron then go?
Line 2.
Line 2. Why not line 1?
Like you said, they're going to repel against each other. So
They would repel against each other. Okay, I like that logic. Where's the next one go?
3,
Next one?
1,
Next one?
5,
Next one?
6,
And
7.
7. Everybody okay with that so far?
Yeah.
Okay. Do I have anybody being like, but wait,
I thought you don't have like, you're talking about like one electron in each orbital?
I said nothing about orbitals.
Each
I've
energy
only said
level?
energy level.
Energy level?
What is the issue with this drawing?
There's only 7 electrons.
There are only 7 electrons.
Yeah.
And according to our periodic table, we can make it up to element 118. And if I have element 118, how many electrons does it have?
118.
118. My theory so far says I can have
118 energy levels.
7 electrons, because there's only 7 rows. So what does that mean about this theory?
It's wrong.
It's wrong.
It's wrong. Something's going on with it. Okay? So we played around with the mathematics behind it, okay? And we noticed that actually they can hold 2 electrons. Okay? And you might say, well, that seems kind of weird. Don't the electrons repel away from each other? And here's this kind of weird nebulous concept that you don't have to understand. You kind of just have to accept. I'm going to draw that second electron in there, and I'm going to draw it like that. Meaning what?
You're going like opposite directions, so chasing each other kind of?
They're spinning opposite directions. Okay? Electrons do repel each other, but if they spin opposite directions, they're like, well, you aren't exactly the same as me. I think I can kind of hang out here for a little bit.
How do you decide
Okay.
which way it's going to spin when you're adding
They agree upon
You-
it beforehand.
You don't want to get into quantum spin states because that's actually computation, and that brings in all sorts of other things. We have very limited control over our spin states, and that is above the level of the course. And if we're going to be really honest, that is actually well
That's
above
smart.
my knowledge.
What happens if you
Okay.
stop moving electrons?
We'll eventually get there, and that's a theoretical limit that we encounter. So 2 electrons per energy level, right? So the third one goes.
This is next 4.
There's 4. Where's the 5th?
1, 3,
6.
3.
Right?
Still no, because you,
That's still wrong.
But now I only have 14,
Yeah.
and I need
118.
118. So something is still missing here. Right? And again, if we fold back into the mathematics of it, we notice there's this pesky other variable floating in there. That as soon as I move up to the second energy level, that variable carries an extra value. What the hell does that mean? Okay. What that's meaning is when I'm at the first energy level, there is only one possible state. Okay. That one possible state means I have only one orbital. As soon as I move to the second energy level, I now have 2 possible states. And it splits into 2 types. What happens when I move to the third energy level? It splits again, and I get 3 types. And the 4th energy level, and the 5th energy level, and the 6th energy level. So on and so forth. They continue to split out.
According to their energy level.
Okay? According to what energy level they're at. So if we're at the 8th energy level, it splits
It doesn't-
to 8 different types.
Oh, there's only 7.
Sorry. 7th energy level, we split into 7 different types.
That's what was the piece of-
Okay? So if we still went through and tried to fill this in, wow, that really doesn't show up very well, does it?
No, it doesn't.
Okay? What happens?
Can you repeat that?
If we propagated this all the way out, and we then tried to put electrons in,
You can put 14 in the 7th cell.
it
wouldn't be enough still.
still doesn't add up.
Yeah, it's too much.
It's too little.
Too little.
Even if we split this all the way out, still doesn't cover all 118 elements. Well, it turns out there's yet another variable that floats out there. And as soon as we hit a particular type, that variable now carries some value. That value causes those sublevels to split. Okay? So our first energy level can't split. So it only has one. The second energy level has an extra value, so it splits. The first one of that, the lowest of it, is a repeat of the type below. The remaining one is a new one. That new one splits, but it splits slightly differently than our initial split. Instead of splitting into slightly different energies, it splits into identical energies because it's the same type, but it's oriented differently. That one splits into 3. I know you're like, what the hell? Yeah, that's okay. That's where we're have to just be happy with and accept. What happens if we move up to the third energy level? And I'll color this in black, so hopefully that's not black.
Oh, that isn't third energy level?
Nope, that was still all our second.
Oh, okay.
Our third energy level we're showing is black,
This is the next
splits into 3 types. Okay. The first one in that set is a repeat down, which was a repeat down. The next one is a repeat of the previous. So the previous one, yes? What?
Does it split then as well too?
That one will also split into 3 because it's a repeat. And then we have that last new one chilling up at the top. Also splits. Well, what does it split into? 1, 2, 3, 4, 5.
So there's like no formula to this. It's
This
just
doesn't make any sense. Like, there's
So, is there a formula to this? Yes.
there is, okay.
That formula is, again, so far above our level of understanding that it makes absolutely no sense to look at. So we might as well say there is no formula, we just have to know it. Okay? Which is really what you need to get out of this. You just have to know it. And you might say, well, where the hell are those numbers coming from? Because this is going to be impossible for me to memorize. Not so fast, because we have a handy-dandy universal tool that organizes virtually all of chemistry for us. The periodic table. All of that information is actually already in the table. It's now just a question of pulling it out. Okay? So let's clean this up a little bit, because I think I've got it. So we got our electron spin. Let's see, did I pull? No, didn't quite. Okay? So we had our orbital type. That was our initial split. And we also encountered something known as an orbital orientation and the electron spin.
Isn't like the
Our spin allowed us 2 electrons. Sorry, that's 2 electrons per orbital. Okay? What's happening as we move up in energy, we add the potential for a new type. New type, new type, new type. Okay? We got some questions down in the front row, so let's run through those maybe.
is it like the row is how many energy levels there are?
We'll get to the organization on the periodic table, yes, but
Okay,
a little bit
I
later.
remember this now.
Do you guys have another question? I know what you're staring at, and
I'm
that's
sure we'll get to it.
back to his
I'm
question.
sure we'll get to it, but it's also it has to do with the.
Yep.
And the group is like the
It's your
last.
periodic table. The organization of the periodic table shows you all of this information. Okay, but before we even get into that, let's see what happens with our orbital types. Okay? So our first orbital type, okay, happens to look like a sphere, okay, which I can only draw as a circle. When I move up in energy, so I'm now at the second energy level, I get a new type, but I also repeat the old type. Okay? So we'll draw our sphere. Before we even draw the next one, let's think back to this sphere shape, because the next part of this is an orientation. If I had a sphere here and I turned it, could you tell that I turned it? No, assuming you didn't actually watch me turn it. There's only one valid orientation for a sphere, which means when I'm looking at that sphere type, I only get one orientation. I only see one orbital. When I move up to the second energy level, I get access to a new type. Okay, that new type looks like a,
Infinity sign.
Figure 8.
okay, we see an 8, we hear infinity sign. None of those is the official word that we're supposed to know for this.
Hourglass?
Dumbbells?
It's a dumbbell shape. Okay?
Weird.
Don't shoot the messenger. Okay? So it is a dumbbell shape that we roughly draw as an infinity sign, if you will. If I took that infinity sign, which is really what we're saying, is if I took a fist and another fist, that is the shape of my p orbital. Ignore my hands or the rest of my arm, just the two fists. That is the shape of the p orbital. It's two fists with nothing in between. So what we're trying to show is where the electron can exist. So when I look at that dumbbell shape, I'm saying the electron can exist in one fist and the other fist, but it can't exist anywhere else. Can't exist in the space between my fists. Well, how does it move from one to the other? Quantum tunneling.
What?
Don't worry about it. It does.
Yeah.
Okay? So that's our shape. If I now rotate, can you tell that I rotated?
Yeah.
Yes. And if I rotate again, oh, snap.
Yep.
Yeah, we can tell that there was a rotation. Right? We said there were how many orientations or how many orbitals for this second type?
3.
There were 3
Oh, yeah.
for that type. There's 1, there's 2, and the third is where? Coming in and out of the plane at us. Okay, so we have 1 on the plane of the paper, 2 on the plane of the paper, 3 stabbing us in the heart because it's just awful. Also known as our X, Y, and Z axes. Okay? That's our orbitals for the the dumbbell shape. Okay? So that's our orientation. The sphere only has 1 orientation. The dumbbell has 3 orientations. If I now want to name this position, let's put a big red box on it. I want to name that position so I can say there is an electron in that spot. How do I name it? It's in the second energy level, and we know that because, remember, we had the numbers on the side initially. It's at the second energy level, and it's the sphere shape. Okay? As Braxton was suggesting, he's inherently lazy. Guess what? So is everybody else. I don't want to write its 2 sphere every single time. So what do I write instead? 2s. I'm now placing an electron in the 2s orbital. Okay. What happens if I now want to reference, keep going away, this orbital? I want to place an electron into that red box. That electron went into what orbital? I now want to say it's that one. Okay. It is going into the second energy level based off of our drawing. Again, look at where this kind of splits out. Yeah? So it is our second energy level. What was the orbital type? Dumbbell. So it's the 2 dumbbell. Dumbbell.
Oh, how are we distinguishing between those 3?
We'll get to that. Okay, there's 3 different orientations. How could I say which one of those dumbbells it was? Well, we did have X, Y, and Z axes. I could call that the 2 dumbbell Z axis, or the 2 dumbbell Y axis, or the 2 dumbbell X axis. That gets a bit redundant and difficult to manipulate because where is the X axis? Please move your hand on the X axis. Where's the X axis now? Depending on the orientation of your observer, what happened to the X axis? It changes. Okay? So we tend to recognize that their importance is with respect to the XYZ axis, but until we define what our viewpoint is, it doesn't really matter. And I can just say, this is the second dumbbell, or two dumbbell, I should be saying.
So then how
Kinda
are you
makes sense?
viewing it only, or what position dumbbell it is only matters once you know how you're viewing it?
Only matters once you know how you're viewing it.
Okay.
How often are you going to be concerned about how you view it?
Nuclear physics?
You will not worry about it. Okay? For this course, or probably if you have to take more chemistry courses, any chemistry course. Okay? You really have to jump up a significant level to actually start worrying about the axes. So there's our next point. We had 2 sphere, and sphere was horrible, so we said 2s. Okay? Here we've got 2 dumbbell. So what do I want to call it? Could go through and call it 2D. Why'd you pick D?
D for dumbbell.
D for dumbbell. That sounds good, except the person that came up with the name for it didn't know how to spell, worse than me. And they called it with a P. It is the 2P.
Nobody bothered to change it?
There's an issue.
You try, but it's already
Okay.
like standardized.
So you could even go through and try, but yeah, you've got standardization issues. The next part, where was all this discovered?
Germany?
What was that?
Germany?
I think most of this was Niels Bohr, and I believe he's German. Does he spell dumbbell with a D? Okay? So we can't just assume the letters match across. Okay? Because we're looking at different languages as our origin. Okay? So let's propagate this, because I have a feeling this is where you guys are potentially going with this. Can I erase what's shown there? Because I need that space. Let's move up to the 3rd energy level. Already getting the deep sizes. Oh my God, really? You can't just accept it? No. Okay. 3rd energy level. The first orbital type will be a repeat. What is that repeat going to be? Our sphere. Okay. If I want to name that sphere, I could call it an S. Is that very clear? No. What do I need to add? The 3, because it's the 3rd energy level sphere shape. Okay. What's the next one up? Our dumbbell shape, which has 3 orientations. The name for each of those orientations independently would be P, but I have to specify that they're at the 3rd energy level. So they're 3P. Okay. Also known as degenerate because they have the same name. Okay. I move up.
This one's 5.
I now have more orbital types, or another orbital type, and that's going to bring in orientations. As Lauren's already suggesting, we're going to end up with 5 orientations. What does that that next orbital type look like?
Fan?
Okay. Fan. There's an option.
Clover.
It's known as the cloverleaf shape.
Oh, that's right.
Okay? So we'll call that our cloverleaf. That could be 3 cloverleaf. Okay? What's our abbreviation? 3D.
What?
Why could we not use D for the previous one? Because we'd assigned D already to the next orbital type. This one has, and I'm not going to attempt to draw this, our 5 orientations. I have a picture that shows it a little bit later, so we'll look at that and kind of challenge that. Okay. After D, what happens? We get F after F, G after G, H, I believe, is how it runs, and it starts to kind of go alphabetical. What's the furthest one we've got? F. F is the highest orbital type we have discovered, at least so far. We could theoretically go further than that, but F is as far as we can get. And believe it or not, that's also stored on the periodic table. We just have to know how to look at it. Kind of makes sense?
Yeah. How many orientations does 7 go up to dumbbell?
7 orientations for the, or sorry, you're saying for the cloverleaf?
No, is it 7 or, no. I'm saying at the 7th energy level.
So at the 7th energy level, we'll have the 7s with 1 orientation, the 7p with 3 orientations, the 7d with, where are we, 5 orientations, the 7f with 7 orientations. It skips E. Okay? So as we scaffold up, that 7th energy level has a lot of potential storage for electrons. Okay? That's going to set us up where now we can account for every element on the periodic table. Okay? Which is going to get us to kind of our next aspect on this, assuming we're okay with everything.
Yeah.
Do you have this like map printed out somewhere, like like the grand of everything laid
The
out?
best map we'll look at some examples. I potentially have some maps.
I have one other question. It's not kind of related, but what is the purpose of creating these man-made elements? Like, what were they trying to accomplish by smashing all these things in?
What's the point of making the tallest building?
Just because.
Because you can.
What's up? There you go. Okay. So if you want that there, it's there, so you can take a picture of it if you would like.
Are we going to
Okay.
need, because you said that it skips, the 7th energy level skips all the ones in between, like the 4th, the 5th, the 6th one, it skips all.
No. You just asked what's at the 7th energy. At the 7th energy, we start with 7s, 7p, 7d, 7f. But we still have to fill everything before it, which is what we're going to get into next. Okay? So let's go ahead and clear everything. I'm going to add some extra stuff here because this was our P, which has 3 orientations. Our P, and then our new D. There's 3, 4, 5. Let's build some atoms. Let's build hydrogen.
Yeah.
Hydrogen's nice and easy. Why is hydrogen easy? It has just 1 electron. Okay? Hydrogen has access to the full spectrum of orbitals. Where's that first electron going to go? Why is it going to go into the first orbital and not, say, the 7th?
It's not occupied,
The 7th isn't occupied either.
There's not the amount of energy to stay there.
Getting at the right idea. It takes the least amount of energy to stay there. What were you saying?
There's nothing to repel that from staying close to nucleus.
Okay. It's nothing to repel it away from the nucleus. When you all came in here, what did you do? You sat down. Why weren't you standing?
It's easier.
It's harder. It requires more energy to stand than it does to sit. What is our natural state? Lazy, we sit. What is the natural state for electron? Lazy, go to the lowest energy possible.
Just energy constant.
Which kind of goes to energy conservation. So if I'm going to draw my first electron, it's going to go in at the first energy level. I now want to be able to tell the world where that electron is without having to draw out this map. Right? So it was the first energy level, right? What orbital type did I have at the first energy level? I only had the sphere, which we call S. Okay? So that first electron went into the 1s orbital. Where do I keep track of the number of electrons in my notations? We vaguely talked about it. The atomic number is the number of protons. Where do we look at our balance of electrons and protons? That was known as our charge, which we really only just said is located in the upper right-hand corner. The upper left-hand corner for our atomic notation was the mass. The lower left-hand corner for our atomic notation was the atomic number. Guess what goes into the upper right-hand corner? The electrons, our information about electrons. Notice the periodic table says no information about electrons because on the periodic table, it is assuming that every single one of those elements is in their neutral state. Okay? So it doesn't concern itself at all with electrons. We just assume they have an even balance. Okay? But the reason I'm mentioning this upper right-hand corner is I want the world to know where that 1 electron is. If I just say 1s, I would then also have to say, well, the 1 electron is in the 1s orbital. How can I change the notation so now that I'm very specifically know I'm looking at 1 electron in the 1s orbital? 1s1. upper right-hand corner, I've now kept track of the number of electrons. There's one electron in the 1s orbital. I have hydrogen. Decent? Helium has how many electrons? 2 electrons. Where's the first electron go? Goes into the 1s orbital. First energy level, the s type. So I could call that 1s1 to explain where that electron is located. Good? Helium has how many electrons? 2. I have to explain where that second electron is. Where does that second electron go? Why does that also go into the 1s and not into, say, the 2s? Each of my orbitals can hold 2 electrons. Right? They're still going to repel each other, right? Wouldn't it want to be by itself further up?
Too much energy then.
There's too much energy to jump further up. I will sacrifice being partnered sitting next to you than going further up because I have to go upstairs to get to that space to be by myself. Right? Electrons are doing the same thing. That next electron will also go into the 1s, so I would say 1s1. If I'm just looking at helium now, could I simplify that? I have the 1s orbital, and in that 1s orbital I have 2 electrons. There's my simplification. Kind of make sense? Okay. Let's not clear all of that. Actually, I'll leave all of that up. We'll make you work on one. Let's do carbon. I want to know where all of the electrons are for carbon. Right? So work it out, see what you can come up with. We'll talk about what you got in a second. If you got questions, just raise your hand. I'll come to you.
2p.
Carbon, 6 electrons. First electron goes where? Whoa. First electron, first energy level. So I would have 1s1. Second electron. 1s1. Next electron. 2s1. Remember, we repeat the previous first before we add the new one. And it's now 2s1. The next one. 2s1. If you like to count. 2p. Next energy level, or the next one. 2p1. Where should I draw that electron in my diagram?
Right next to it?
So I'm hearing an option, we'll color it in red. I'm hearing an option to put it here. That's Braxton's suggestion. Kind of throwing you under the bus, sorry. You at least volunteered. Okay, and I'm hearing another suggestion that I should go over here. Ooh, crap.
Makes sense.
2 choices. Where should the electron go? Okay, the second option is the better option. I should be putting it here. Why here and not paired? The only reason we pair is there's not a lower energy or equal energy state for me to go. Okay, I'd have to move to a higher energy. As soon as I hit the p orbitals, all of those orbitals are at the exact same energy level. So I will fill each of them half first and then pair if I have to. Okay? Which is a really kind of bizarre extra step on this. This is an upper tier kind of level question that becomes relevant when we look at ionization energies and other things further on down the road. It is not officially something that you need to get through the class. Okay? It's an explanation aspect that's important for later on. Okay? If we were to write it out, it just becomes 2p1. Where's the next electron? We don't have it, right? We've got our 6 electrons. Okay? So we could have just gone through and done all of that nice and stepwise. Okay? We could have also just said, well, I know the 1s energy level can hold 2 electrons. I know the 2s energy level can hold 2 electrons. And the 2p can hold 6, so I could just write 6 there.
But you only have 2 more left.
I only have 2 electrons that I can place into that. How do I have a check to verify that I actually did carbon and not something else? What was written in the upper right-hand corner of all of those symbols?
The amount of electrons.
The amount of electrons. So 2 electrons plus 2 electrons plus 2 electrons gives me 6 electrons. How many electrons did neutral carbon have? 6. It counts, or it checks out. Make sense?
It only has 2 valence.
Okay. Don't open that can yet. We good? Yes?
So when I wrote mine out, or I guess I should phrase it, when we do it on the test, do you want it written out as like 1s1, 1s1, 2s1?
Nope. What I would expect is the shorthand that we've given down here. 1s2, 2s2, 2p6. Okay? I don't expect all of this written out. I'm just showing it so that you see where everything is going. Make sense?
Once you learn the order of which things are going to be filled in, it'll actually become pretty easy.
Once you've got the order, yes, it becomes very straightforward. You memorize your order and you just fill them in. Yep, exactly right. Okay, other questions on it?
Is this like what questions on the test are going to be like?
A question on the test,
how many?
it would be multiple choice, can't be show your work because there's really no work to show. It would say which of the following is the correct electron configuration for nitrogen.
Yeah. So there's-
You got 5 multiple choice answers. One of them is the correct one. One of them is incorrect, or 4 of them are
So it
incorrect.
would be the same as this instead of 2p3.
Yeah, so if I did nitrogen, what changes about this formula?
You just add them.
I add 1 more electron because nitrogen has 7 and it becomes 2p3. Everything else holds constant beforehand. Kind of make sense?
Yeah.
He just said that it technically, like, we're not gonna do what you need, but, yeah.
Okay. That's how you fill individual orbitals, yeah. Well, this is awkward. Lee recorded. I don't remember what I was going to say next.
Next slide.
Kind of don't think so, but that's just what we're gonna, maybe I think I know where I'm going. So ultimately, all we're doing with this notation is deciding where the electrons live. And everybody goes, oh my God, this is so hard, I can't do this. Okay, you've already done this in your lifetime. Okay, if you're telling somebody how to get to your house, what information do you give them? The number
Your address.
on the street that you live at, the city, the zip code, theoretically the nation, okay? All of those pieces are narrowing in on the exact location. That's what we're doing with this. Our energy levels are effectively the nation, okay? The orbital type, the city, if you will. The orbital orientation, the street within that city. The electron spin is the actual number on that street. Okay? It's merely an address for where everything is located. Some addresses make sense, some don't. Okay? But that's what we're working with. It's just a location. Okay? Yeah, I'm still thinking I'm missing something, but we'll just have to run with it. Our orbital types, we said the S, the P, and the D. Right? Those were our shapes. The S, when I look at the S on its own, how many orientations are there? 1. Doesn't matter which way I orient it, it's always going to look the same. That means there's only 1 orbital. Only 1 representation for it. When I move to the P type, what happens? I now have different orientations. I can move them onto different axes. What happens when I move to the D type? Okay. I get a lot more orientations, and you might try and go through and do the XYZ thing. Wouldn't there only be 3? Well, there are your other orientations. Okay? The first 4, you might be like, okay, I kind of see what you're doing. You're running kind of off of the axes on those angles. Why would you have to run off of the axes is not directly on the axis? That's a pretty advanced question. Okay. If we take a look, let's see if I can pick. No, mother
You said
of
they can't
God.
exist, but then like it's only like one of these little orbitals up there, and so
Okay.
it can't be touching. So that's why it has to be right. Like the.
If we draw in our p orbitals, there's a p orbital on the z-axis. I'm not trying to talk over you, but you are saying it. There's one on the y-axis. There's one on the x-axis. There's already an orbital on that axis. If the d orbitals were oriented onto that axis, they would then be overlapping with another orbital. You're putting more electrons into the exact same space. Can we do that?
No.
No.
So the axes are where there's already energy.
Because of the previous orbital orientations, yes. So that's why our d orbitals are not directly on those axes. They're off-center.
They run along.
Okay? They're running kind of on the edge of that so that they don't overlap with the p orbitals.
Like parallel and perpendicular then,
Sure.
right?
I definitely don't have the spatial awareness to see it. All I'm saying is it's different. Okay? So that kind of explains those 4 types. Does that look like a clover leaf?
No.
For those at home that might not be able to guess at what I'm pointing at, does that look like a clover leaf? No. Okay. It's usually called the dumbbell with a donut. Okay. Is that a clover leaf? No. Is it a d orbital orientation?
Yes.
Yes. Okay. The orientation is really our hand-wavy way, or my hand-wavy way, of trying to wrap our brain about those different options coming out of it. Okay. It's not officially an orientation. It's officially a quantum mathematical solve from that stupidly difficult stuff that we don't want to look at. Or rather, I don't want to look at in front of you. Okay? The d orbitals, we end up with that last one, the dumbbell with a donut. Okay? It's just there, you have to be aware of it. Okay? So, capacity within our orbitals. This was our electron spin. Each orbital can only contain 2 electrons. Okay? So what we want to do is now go through and say, well, as we fill, how many electrons can we possibly get in? So for that first energy level, how many electrons can fit?
2.
Okay? 2. I have the sublevel, or my orbital type, being S. Okay? There's only one orientation, so there's only one orbital, and I can only put 2 electrons in. So within that orbital, I have a whopping total of 2 electrons. Within the energy level, well, that's it. There's no other orientations. Within the energy level, how many electrons do I have? 2. That's it. Okay. What happens if I move to the second energy level? I get the 2s and the 2p. How many electrons can I fit into the 2s orbital? 2. How many electrons can I fit in an 2p orbital?
And what?
4.
Right. Said another way, how many electrons can I fit in a single 2p orbital?
1.
2. How many 2p orbitals are there? 3. Which means in the 2p sublevel, how many electrons can I fit? 6. You might say, well, isn't that a really nuanced way to ask the question? Yes, I do think that is slightly dumb, okay? But it is an important enough distinction that comes out of your ability to read the question that is really important. Okay? So be careful to answer the question that is directly asked of you, not the question you want to answer. Because in a multiple choice test, both 2 and 6 would show up as answers. Okay? Probably also 3. How many electrons fit into the second energy level?
8.
Now it's 8. Why did I not say 2 or 6? Because in the second energy level, it's any orbital that has the 2 in front of it. I have both the 2s and the 2p. Make sense?
Yeah.
Okay. Third, I have the 3s, 3p, 3d. In the s, I have 2. In the p, 6. In the d, okay. In the d, I had 5 orbital orientations. Each orbital carries 2 electrons, meaning 10, which gets me 18 electrons. Okay. Next level. 1s only fits 2 electrons. Okay? Which means I can really only explain two elements in their neutral state with the 1s orbital. Which two elements could I explain using only the 1s orbital? Hydrogen and helium. Let's take a look at hydrogen and helium on the periodic table. What can you tell me about them with respect to each other?
They're next to each other. Like,
Is everybody saying yes, they're next to each other? Okay,
They're all
so
the
I know
same-
what you're trying to say. Yes,
They're all
keep
the
going.
same height.
Same height, I
They're all
can
the
sort of
same
give that.
Y-axis.
Same row, the same series, the same period. Guess what that period corresponds to? The first energy level. How many elements showed up in the first energy level? 2, corresponding to the 2 electrons that I could fit in this first energy level. Well, that was easy. There are only 2 things there, so that trend can't possibly continue.
Yeah.
Let's move to the second energy level, which we would say would be the second row. How many elements are in the second row? 8. How many electrons could I fit in the second energy level?
Hey. What?
You ready for the big one?
Let's do it.
Third energy level. How many columns in the third energy level on the periodic table? 8. And there are...
18.
What happened?
We almost had.
Someone messed up.
It's not a rule, it's a trend.
Move to the fourth energy level. 18. What is going on here? Scandium to zinc were known as the transition elements. Okay, they're transitioning between our alkali and alkaline earth over across the other side. Okay, which was our chalcogons and all that fun stuff. Okay. Well, that means we'd have to know all those names, and that doesn't seem to make sense. Turns out there's another thing that we can build out of this periodic table that can help us out. If we looked at the electron configuration for hydrogen, what did we have? It was 1s. What is the electron configuration for lithium? 1s1. It would be 1s2, 2s1. What is the electron configuration for sodium? Whoops. Anybody notice anything interesting? That outermost section is all filling S. And I'm filling only 1 electron into it. Interesting. What happens if I move it to, instead of being lithium, I make it beryllium? 1s2, 2s. 2.
P6.
Beryllium.
Oh.
No.
Probably.
There's no D. We'll get back to that. What's the next element I might check? How about magnesium? What would magnesiums be? 1s2, 2s2, 2p6, 3 s2. What if I jump to boron? One s2, 2s2, 2p1. What if I jump to aluminum? 2s2, 3p1. The gap that we're seeing there, where the transition elements are sitting, is the transition between the s orbitals and the p orbitals. If you section off those first 2 columns, those will always have or end with s orbital types. If we jump over to boron, everything to the right of boron will end within those columns with p type. What are the transition elements going to be?
D.
The D type. Lanthanides and actinides? The F type. Okay. this still doesn't quite resolve what happened with our third energy level, right? Because we said the third row only has 8 electrons. Well, what's going on there? Okay. Well, let's go back through that. Let's start with argon. Why would I pick argon? Remember, I'm concerned about the third row. Argon is the last in the third row. So if I looked at its electron configuration, 1s2, 2s2, 2p, 6, 3s2, 3p6. The very next electron I would expect to place where? According to everything we've talked about so far.
21. So SC.
I'm hearing a lot of people saying 4s. Is that what you agree with? We moved from the first energy level with S. We moved to the second energy level. We repeat the orbitals, S and P. We move to the third energy level. We repeat. We get S and P and D. Wouldn't you expect the very next electron after argon to go into the D orbital? We would expect that, right? At least I kind of expect that. And yet, if we add one more electron, we would become what element? Add an electron, we would become potassium. And if I look at the electron configuration for potassium, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Remember, potassium is in that first column. It has to end with S. And because it's in the fourth row, it needs to be the fourth energy level.
Yeah.
If you count that up, that should be 19. Right, so we got 19 electrons. Why did I not go to the 3D?
Because it's not, the 3D is not the first one. It's easier.
It messes things up. What's going on? What's happening? Well, remember, as we moved up in energy, what happened? So this is my first energy level. The second energy level is, let's go here. Here, right? Where's the third?
Closer.
Above it, but closer.
Above it, but closer. The fourth?
Same.
Above it, but closer. Remember, as we filled first the lowest energy, and then we moved up for a pairing situation. Okay, we stayed at the same energy if we could stay unpaired. What is the difference in energy between the 4s energy level and the 3d energy level?
Very minuscule.
They are so minuscule that something else jumps in there. That something else comes down to a choice. If I look at potassium, it fills the 4s first. So here's my 4s. This is what it would look like with one electron in it. If it had instead gone to the 3D, 1, 2, 3, 4, 5, these are my 3Ds, right? Everybody agree? If it had gone to the 3D, it would have looked like this.
So is it
Do you
easier for it to go to the S?
see a difference? What is that difference? And it's not necessarily any easier. This is another one of those mind explosions. Close your eyes. Seriously,
So-
close your eyes because it's creepy if you stare at me for this.
If there's only one,
Close your eyes.
then
Close your eyes. Envision the most perfect person you've ever seen. This is why you don't stare at me. Okay? Cover half their face. Okay? Cover the other half of their face. What do you notice about their face?
It's not symmetrical.
In most cases, it happens to be symmetrical. Okay? If you look to every society, you can open your eyes now. If you look to every society, we tend to settle on symmetry. The more asymmetrical the person becomes, the less beautiful, attractive, handsome they are. Okay? And you might say, well, I'm not that shallow. You are. Sorry. Okay? You can even pick like famous people. Cindy Crawford, if anybody remembers that, with the mole, right? She had a mole. Everybody's, oh, she's gorgeous, but she's asymmetrical because of the mole. Remove the mole, how asymmetrical is her face? Snap, it's like a perfect mirror image. The one imperfection was enough to make her beautiful or not ruin it. Okay? Same thing's happening with our electron orbitals. Symmetry plays a really important role. I am half filled, but in only one spot. One spot is half filled, the rest are empty.
1 out of 10.
4s is more symmetric with one electron than the 3d is with one electron. So what does chemistry go through and do? It says, well, I can be more pretty if I do half filled for one orbital than half filled for just 1 out of 5. So what do? I fill the 4s first. I move to calcium. 4s2. I move to scandium.
3D.
Oh, now I got a ton of electrons to add in. If I move up to the 4p, it's too large of a jump for me. Symmetry is now out the window. I'm going to fill in my 3Ds.
So it's only for the sake of symmetry that you
It
need
is
to add.
only for the sake of symmetry that our filling changes at that point.
But
Why did the periodic table not organize better so that we could see that? Why didn't we say the transition elements were right after argon? So that we could see that the 3D fill differently.
Same things before, not aesthetically pleasing.
They did. They did account for that. They said the 4s fills before the 3D. If you follow atom by atom all the way through, what comes after argon? 4s, not D. The order on your fill rate, on which orbital you need to fill, is already embedded in the periodic table. You don't have to memorize the pattern. You do have to memorize that the transition elements are offset by 1. The f orbitals would be offset by 2. They're offset by 1 because of the d orbitals, and they're offset by 1 by nature of their characteristics. Do we have to worry about filling 60 electrons into our electron configuration? No, why not? Because it's 130, I don't want to deal with that crap. We deal up with the 4th row, and that's about it.
What's the
Okay.
4th row type again?
Our 4th row, we get S, P, D, F. So at our 4th energy is officially where the f orbitals come in, but they're offset by 2 because of the fill rates. Really goofy. Okay. The last thing I wanted to get through, you may see something like this. Okay. Rylan was asking about, is there a pattern that shows this? You've got a filling diagram. You could go through and do like needlework. You fill on the diagonal. 1s, ooh, I loop back around. 2s, ooh, I loop back around. 2p, 3s, ooh, I loop back around. 3p, 4s, oh, I loop back around. 3d, 4p, 5s. That can also explain it. So you could memorize this extra thing, or you could just read the periodic table. It's kind of how I see it. And I promise, last thing, valence electrons. The valence electrons are referring to your highest energy level in your electron configuration. So whichever number is the highest, how many electrons are in that highest energy level. Okay? The rest of them I won't worry about, because the electrons are what are doing the bonding. That's our next unit, looking at chapter 12. Not our next unit, but our next kind of big thing, chapter 12. If I want to interact with you, I'm going to interact with my hand, not with, like, my liver. Okay? We aren't concerned about how our livers touch each other, because that would not be pleasant. Okay? We're more concerned about how our hands are, because the hands are on the outside. We're concerned about the outermost electrons. And I do apologize. I definitely